In this video, we're going to take a look at the first derivative test for local extrema. And so let's go ahead and do that here. So we're going to suppose that C is a critical point of a continuous function and that f is differentiable at every point on an open interval containing C, except possibly at C itself. And then one of three things can happen. If f prime changes from negative to positive at some value C here, or at this value C, then f has a local minimum at C. If f prime changes from positive to negative at C, then f has a local maximum at C. And if f prime does not change, then f has no local extrema at C. Let's take a look at what that means relative to a picture. So we have some picture here. And on this picture, we have two local extrema. And notice to the left of this extrema, of this critical value, our slopes are positive, so our function is increasing. So our derivative is positive. On to the right, our derivative is negative, the function is decreasing. And notice we go from increasing to decreasing. We have a local maximum here. If at this point we go from decreasing to increasing, then our function changes and has a local minimum. And that's what these first two statements say. Now suppose we have something like y equals x cubed, which would look like this. Right here, we have a horizontal tangent line, so y equals x cubed, the derivative is 0 at x equals 0. But to the left, we have an increasing function, so a positive slope. To the right, we have an increasing function, so a positive slope. Notice it doesn't change, it's positive and then positive again, and so we don't have a local extrema there, as in there's no maximum or minimum at that point. And that's all this first derivative test right here tells us, is those three things. I just want to end this video with one example where we calculate that for a particular problem. So we have an example here, and we want to find the local extrema and the intervals on which f of x equal to x cubed over 3 minus 2x squared plus 4x is increasing or decreasing. Okay. So let's go ahead and do that. Well, first, just like before, we want to find our critical points, and we do that by taking the derivative. So f prime of x is equal to 3x squared over 3, that just reduces to x squared, minus 4x plus 4, which we can factor into x minus 2 times x minus 2. Hey, we only have one critical point here, and that is c equal to positive 2. This breaks up our intervals, or breaks up our domain into two intervals, and that is the interval from negative infinity to positive 2, and the interval from 2 to positive infinity. And it looks like we only have really one factor, but it is squared. So that will tell us what happens with the derivative, which will then tell us what is going on with the original function. Okay, we plug in something from negative infinity to 2. Let's plug in 0. If we plug in 0 here, we get a negative, but then squared is a positive, which tells us our whole derivative is positive, which tells us that our function is increasing. Okay. And then we have 2 to infinity. All right, so let's plug in 5. All right, that is positive here. This gives us that the derivative is then positive, and so our function is increasing. Now, this point right here, this value right here is representative of our critical value c equals 2. So we want to know, does this point, is that a local maximum, a local minimum, or is it neither? Well, to the left of this point, we are increasing. To the right of that point, we are increasing. So that tells us that since this didn't change, c equals 2 is neither a local max nor a local min. So we had no local extrema in this particular example. And again, what was the other thing we wanted to know? We just wanted to know where our function is increasing or decreasing. So this is increasing on negative infinity to 2, union 2 to infinity. So everywhere, if we include the value 2. And that is it for this particular video.